In physics, there's a set of laws called the laws of thermodynamics. Now, these laws outline the way that heat and energy act. The first law states that energy cannot be created nor destroyed in a closed system. It can be stored, changed, transformed, converted, moved, but it can't come out of nowhere and it can't just vanish. It has to come from something. Let's take a pendulum, for example. If you have a 1 meter pendulum and a 1 kilogram weight at the end of it, at the top of its swing, there will be 9.8 joules of potential energy. Once you let go, it'll turn that energy into kinetic energy. Then it'll turn back into potential on the other side. Now, according to this law, there must be the same amount of energy at the end as there was at the beginning. So the pendulum should reach the same height each time and swing forever. However, this isn't quite the case. If you actually measure the height at each end, it's a little bit shorter each time. We're losing potential energy. Now, that energy can't just vanish, so it has to be turned into something. We lose it to heat. The pendulum moves through the air, and the string pulls on the pivot point. Now, both of these things create friction, which converts our kinetic energy into thermal energy, also known as heat, and it dissipates into the room. Energy often converts into heat, but heat very rarely converts into usable energy. Now, humans have created heat converters known as thermoelectric generators. However, these are not 100% effective because of the second law of thermodynamics. The second law states that entropy in a closed system will always go up. Now, entropy is a bit of a complicated subject, but it sort of means chaos or disorder or complexity. Let's take food coloring, for example. If you just drop food coloring on its own, it becomes a small little dot, very low entropy. However, once you put it in water, it scatters about, it spreads around, it becomes high entropy. It takes energy to turn chaos into organization, but it takes nearly no energy to take organization and let it turn into chaos. This is why entropy always rises. A car is a great example of heat conversion and heat loss. Imagine if we put a thermoelectric generator on top of a car. The heat that leaves the car will power the generator and re-enter the car through a wire. Actually, no, some of the heat will go through the generator, also the wire leaks some heat. Okay, new plan. We'll put a generator on that generator and a generator on that wire. Then we have to connect it with the wire. Okay, new plan. Put a generator on that generator, then a generator on that generator's wire's generator. Then we'll put a generator on that generator's generator. Then we'll generate that generator's generation power with generated wires from generated generators. You'll never get 100% of the heat, ever. It escapes faster than you could ever collect it. But you can get some of it. There's a fabric, thermoelectric material, that when car exhaust passes through it, the electrons get caught and charge the material. Now, about 20% of the energy that goes through it can be converted into electricity, and 40% of a car's heat is released through the tailpipe. So 8% of the energy from your car goes into this fabric. That's great, but remember, your car doesn't necessarily run off electricity, so it needs to be converted into a form your car can use. Let's say we lost 20% of the energy into this conversion to heat. Now, that's an optimistically low number, but let's run with it and see where it takes us. So that equals 6.4%. Now, 6.4 isn't a lot, but it's not nothing. Especially once you're talking about all the cars on Earth, it really starts to add up. There's over 1 billion cars on our planet, each one being driven about 13,000 miles a year, with an average of 25 miles to the gallon. Now, overall, that's 520 billion gallons of gas being used each year. Now, if we saved 6.4% of that, we would be saving 34 billion gallons of gas each year. That's enough to fill 43.5 football stadiums. Now, this is great because it can happen. It's not just theoretical. All of these numbers can come true. Maybe not right now, but this technology is only going to get better and cheaper, especially if we focus more on it like I think we should. And don't worry, this fabric isn't the only thermoelectric generator. There are many more out there, and there are many more to come. But it's important that we focus on them now, because they really can change the world. Remember the example with the pendulum? We only lost energy to heat. If we could turn that heat back into usable energy for the pendulum, it would keep swinging for longer, much longer, maybe even indefinitely. We're talking about having enough energy for long-distance space travel, for phones that last for years on a single charge. We're talking about advancing humanity to a point where burning fossil fuels or breaking nuclei for energy seems as outdated as the idea of quills did after pens.